So what is meant by a cyclic quadrilateral first of all? Now, if you see in the figure, let me make this a little bigger so that you are able to see this clearly. Fine, this. Okay, now if you see in this figure, ABCD is a quadrilateral whose vertices are lying on the circle, right? They are all on the circle, A, B, C, and D. Vertices are all on the circle. Therefore, the definition of a cyclic quadrilateral is that any quadrilateral whose vertices lie on the circle is called a cyclic quadrilateral. Okay, so in this figure, ABCD is a cyclic quadrilateral. Okay. Furthermore, there's a definition which is called as the concyclic points. Concyclic point. Now, what is the definition of concyclic points? If ABCD is a cyclic quadrilateral, then the points A, B, C, and D that you see in the figure, these are called concyclic points. The points that lie on a circle are called concyclic points. Okay. Okay. Now, three theorems I had discussed under angle property. So that is why this is called theorem number 4. Okay. The theorem is the sum of either pair of opposite sides of a quadrilateral is 180 degree. Okay, that means the sum of these two angles, opposite angles, will be 180 degree. This angle plus this angle. These two are opposite angles of the cyclic quadrilateral. The sum of these two will be, if you add the two angles, it will always come out to be 180 degree. Okay. Similarly for these two also, let me draw it with a different color. Similarly for this angle and this angle also. If you always add these two angles, these two will always come out to be 180 degree, the sum of these two. That is what is meant by this theorem. Okay. And see, that is what I have written here also, that angle A plus angle C will always be equal to 180 degree, and angle C plus angle D will be equal to 180 degree. Very important property which we shall be using in the sums. Okay. Fine. Based on this, I have given you a sum. So let's see this sum. Okay, look at this. I hope this is visible, or should I make it big enough? This should be okay. Okay, in this figure, O is the center of the circle. Okay, so I know here that O is my center here. Find X. You need to find this unknown angle X. Okay, now I have drawn this figure once again so that you know that while doing in your examination, if any figure is given, you redraw that figure and then you write. Okay, so how am I going to solve this sum? Look at the figure. First of all, because I have written this, you can go through these notes. Okay. First of all, since O is the center, this angle that is made here, this is angle in a semicircle. That means this angle must be 90 degree, right? So this angle is 90 degree, angle in a semicircle, right? Once I know, now look at this triangle, triangle ACB, right? In this triangle, you can find out this angle because you know two angles of the triangle, which is 180 minus 90 minus 25. And this should come out to be 65 degree, right? Now, once you know this angle, now you see that ABCD is a cyclic quadrilateral. And which ones are the opposite angles? Let me write it here, 65 degree. Now you see that in this cyclic quadrilateral, these two are opposite angles, right? Right. Also, what are the other opposite angles? This angle and this angle is the opposite angle, right? But we are not concerned about the other two. We are only concerned about, because we need to find X, we are only concerned about these two angles. So the sum of these two angles is 180 degree. That means what will happen? I must have X plus 65 equal to 180 degree, right? That means X must be equal to 180 minus 65, which should be equal to, I think, 115. Yes, 115. Clear? Moving on to the next one. Now the converse of this theorem. Now in the theorem, it was given that if ABCD is a cyclic quadrilateral, the sum of the opposite angles of the quadrilateral is equal to 180 degree. In this case, it is given to you that ABCD is a quadrilateral such that the sum of these two angles is 180 degree. Then can we say that ABCD is a cyclic quadrilateral? Yes. If you see that in any quadrilateral, if you don't know whether the ABCD lie on the circle or not, but what you see is that the opposite angle, any pair of opposite angles of the cyclic quadrilateral, you see is the sum is 180 degree. Then you can say that ABCD must be a cyclic quadrilateral. Okay, this is the converse of the theorem. Okay, so if in order to prove, if you are asked for any quadrilateral, prove that this is a cyclic quadrilateral, you just need to show that the opposite sides, opposite angles are, the sum of the opposite angles is 180 degree. Okay, let's do the next one. Next theorem. The next theorem is an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Important theorem once again. Okay. Now, what does this theorem mean? It is given to you that ABCD is a cyclic quadrilateral. And what I did is that I produced one of the sides and formed an exterior angle. So this becomes an exterior angle of cyclic quadrilateral. Okay. This is the exterior angle of the cyclic quadrilateral ABCD. What can be the other exterior angles? If I produce this side, this will be another exterior angle, right? If I produce this side, this will be another exterior angle, right? You will get 4 exterior angles. If I produce this side, this will be another exterior angle, right? So I've just produced one exterior angle. I just made one exterior angle by producing one of the sides. Okay. Now, according to this theorem, this exterior angle will be equal to the interior opposite angle. So if you see, the corresponding interior angle is this one, and opposite to this interior angle is this angle. These two angles must be equal, right? So you have the exterior angle of this. If this angle is x, this angle will also be x, because these two are, one is exterior angle and the other is interior opposite angle. Okay, interior angle and opposite, right? So what can be the, if in the same figure, if I am to say this angle is x, then which other angle will be equal? Interior and the opposite. So this one will be x. Okay. If I am to make another exterior angle, I produce this side and produce this an exterior angle, this, which angle will be equal to interior angle and the opposite? That means this angle will be x. Okay. So this is the meaning of this theorem. A problem based on the theorem. Let's see what the problem states here. Okay. In this figure, O is the center of the circle. Find x. Okay. So O here is the center. You need to find the unknown angle x. This is what you need to find. So how will I proceed with this? Which angle is given to me? This angle is given to me here, 80 degree. That is what we must note. Okay, so now when we redraw the figure, we'll see that if this angle is 80 degree, and you see ABCD is a cyclic quadrilateral, right? A, B, C, D. This is a cyclic quadrilateral. And in this cyclic quadrilateral, 80 degree, this angle here is the exterior angle. That means which angle must it be equal to? This angle, the 80 degree, must be equal to this angle. So this angle must be 80 because of this theorem, because the exterior angle of a cyclic quadrilateral is equal to its interior opposite angle. So this angle is 80 degree. Okay, so once we know this angle is 80 degree, now what can we do? You know this angle is 80 degree, then this angle here is angle at the center on which arc? This arc BD, right? And you have angle on the remaining part of the circle as 80 degree. This one, this angle 80 degree. So that means you know that the angle, this is 80 degree. You know that the angle subtended by an arc at the center is double the angle subtended by it on the remaining part of the circle. So this 80 degree is the angle on the remaining part of the circle. So therefore this angle here must be double of 80 degree, must be 160 degree, right? So what should be x? Because you have one complete angle here, 360 degree. So x will be equal to 360 minus 160, which is equal to 200 degree. Okay. So x is 200 degree. Fine. Moving on to the next question. Next, in fact, the converse of the theorem is left. Let's see what the converse of this theorem states. The converse of this theorem states that if an exterior angle of a quadrilateral, any quadrilateral, is equal to its interior opposite angle, then you can say that the quadrilateral is cyclic. In the main theorem, we were saying that if cyclic quadrilateral is given, if a quadrilateral is given to be cyclic, then we can say exterior angle is equal to interior opposite angle. But in the converse, we are just interchanging the given and the conclusion. That is, if it is given to you that exterior angle is equal to one of its interior opposite angle, then you can conveniently say that it is a cyclic quadrilateral. Okay, that is what the converse of this is. Fine. Okay, so let's move to the exercise part. Some more problems on cyclic quadrilateral, cyclic properties of circles. Okay, so let's see this first problem. Okay, in this figure, angle DBC is 58 degrees. So I have marked it here. DBC is 58 degrees. BD is the diameter. That means this line that you see here, this is the diameter. That means the center of the circle lies on this line. Okay. Remember that this line here passes through the center of the circle. Okay. You need to calculate angle BDC. So how do you calculate angle BDC? First of all, since BD is the diameter of the circle, you can say this angle is 90 degree, right? Because angle in a semicircle, BD is the diameter. Angle in a semicircle, that means this angle must be 90 degree. And if this angle is 90 degree, now if you look at this triangle here, if you look at this triangle here, triangle BDC, this triangle, BDC is nothing but the third angle of this triangle, right? So this angle here will be equal to 180 minus, because the sum of the angles of a triangle is 90 degree, 90 plus 58, isn't it? Right? Which is equal to 32 degree. And that is what I have done. Okay. Moving on to the next one. So we have found what angles? Let me write it here so that we know we have found these angles. This angle we know is 90 degree, and this angle we have found out to be 32 degree. Okay, proceeding to the next question. Angle BEC. Now BEC, how will you find BEC? If you see BECD, that means the quadrilateral formed by this is a cyclic quadrilateral, right? All of them lie on the circle. That means the sum of opposite angles must be equal to 180 degree. That means this 32-degree angle that we have found, sum of this angle and this angle, the unknown angle that we need to find, must be equal to 180 degree. So that means you must have angle BEC plus 32 must be equal to 180. So that means what is angle BEC? Angle BEC is 180 minus 32. Okay, which is equal to 148. 148 degree. Okay, so we'll write here 148. Whatever angle we have found, we'll write 32. This is 90. This is 148 we have found, right? And the last question is angle BAC. Now this is the easiest one. Angle BAC, if you see these two angles are angles on the same segment, isn't it? What is the segment? This segment, right? They are angles on the same segment. So therefore, this angle will also be equal to 32. So therefore, angle BAC must be equal to angle BDC, which is equal to 32. Okay. Moving on to the next question. Let's see. In this question, you have in the figure given below, AB is parallel to DC. Okay, so it is given here that these two lines AB and DC are parallel, which I have marked. Angle BCE is 80 degree, so this angle is given here to be 80 degree. Angle BAC is 25 degree, so this angle is given to be 25 degree. Okay, what do we need to find? First, we need to find angle CAD. Which one is angle CAD? This one is angle CAD. We need to find this. How will I find? First of all, see, this angle is 80 degree. Also realize that ABCD is a cyclic quadrilateral, right? Because they'll all lie on the all the vertex lie on the circle. Each of ABCD lie on the circle. So therefore, this is the exterior angle of the cyclic quadrilateral. It must be equal to the interior opposite angle. That means this entire angle here is 80 degree. If this entire angle is 80 degree and this angle is 25 degree, what should be this angle? 80 minus 25, which is equal to 55 degree, right? So CAD angle we have found. That answers the first question. So let's write what we have found. Let's write this as 55 degree. Okay. Next, angle CBD. How will you find out angle CBD? If you see CBD and CAD, both are on this segment, right? So therefore, this angle will also be equal to 55 degree. So that is a one-line problem, one-line question. The CBD is also equal to 55 degree. CBD is equal to CAD equal to 55 degree because they are angles on the same segment. Next, angle ADC. How will you find out angle ADC? Now, this is also very easy because this angle here, this entire angle, as I told you in the beginning, is 80 degree, right? And these two lines are parallel to each other. So therefore, this entire angle, this 80 degree entire angle and this angle must be co-interior angles so that the sum will be equal to 180 degree, right? So therefore, angle ADC plus 80 degree must be equal to 180 degree because they are co-interior angles. So that means angle ADC will be equal to 100 degree. So this angle here, its value is 100 degree. That answers the third question also. Okay. So I'll proceed to the next one then. Okay, look at this question. In the figure given below, O is the center of the circle. Okay, so O here, if you see, this is the center given. Angle AOE is 150 degree. I have marked here in this angle here, AOE is 50 degree, 150 degree. Angle DAO is given to be 51 degree. This also I have marked in the figure, 51 degree. You need to calculate angle BEC and EBC. So let's see which angle we have to find out first. You need to calculate angle BEC. That means this angle you need to calculate, right? So first, how will you calculate BEC? If you see ABED, all these four, they all lie on this circle. So ABED, this quadrilateral that is formed, is a cyclic quadrilateral formed by these. And if you see BEC is the exterior angle of the cyclic quadrilateral. And which one is the interior opposite angle? This one. So these two angles must be equal. So this will also be 51 degree. Okay. Let's write this. We have found out this angle to be 51 degrees. Next, angle EBC. EBC is which angle? This angle here is EBC. How will you find out angle EBC? EBC, if you see, is the exterior angle of the same cyclic quadrilateral, ABED, right? And what you see here is that this angle EBC must be equal to this angle. But what is this angle equal to? How will you find out this angle? Okay, that is the question. If I can find out this angle, then we can find out EBC. Okay. Now, how do you find out? Look at this. You have here, if this angle is 150 degree, what will be this angle? 360 minus 150, right? Which is equal to 210 degree. And if you see, this angle here is on this arc, right? Is on this arc. Angle subtended by this arc at the center is 210. And what is the angle subtended on the remaining part of the circle? This one. So this angle will be 210 divided by 2, which is equal to 105, because angle subtended by a circle at the center is double the angle subtended by it on the remaining part of the circle. So this 210 by 2 angle is angle subtended by the same arc, AE, on the remaining part of the circle. And once we know this as 105, this angle will also be 105, because the exterior angle of cyclic quadrilateral is equal to its interior opposite angle. Okay. This is one way of doing it. In the problem in the solution, I have done it another way. You can go through that way also, but this is the easiest way of doing it. Okay. And I'll stop here.